Hello everyone, a very good evening to all. Myself Vivekananda Nayak, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I welcome you all once again for this 11th interaction session on the course Atomic and Molecular Physics, which is being flowed this January 2026 session with course code Energy 26 PH 18 by NPTEL. Today we'll be uh, mainly discussing about a few sample problems covering the week 11 course content of the course content of lectures. So, if we talk about the so before solving a few sample problems, let's discuss briefly about the concept covered in this week's lectures. So, if we talk about week 11, it was electronic spectra of molecules. So, we in the previous 2 weeks we discussed about the different types of spectra like which can be exhibited by molecules like rotational, vibrational. So if you talk about different spectra and the order of their energy, so rotational spectra, rotational spectra, the order of their energy is 10 to the power minus 1 centimeter inverse. Vibrational spectra 10 to the power 3 centimeter inverse, and electronic spectra 10 to the power 5 centimeter inverse. So the maximum energy corresponds to electron spectra, then vibration spectra, then rotational spectra. And if you talk about the total energy of a molecule, so del E total equals to del E electrical plus del E rotational plus del E vibrational. Now, if you talk about different types of molecules who exhibit rotational and vibrational spectra, sorry, there are some disturbances. So now, if you talk about the uh, different type of spectra that we already discussed, we discussed that there are few molecules that don't show rotational spectra. There are few molecules that don't show vibrational spectra. So if we discuss that, so now if we talk about pure rotational spectra, pure rotational spectra. So these are the molecules who have permanent dipole moment. They show pure rotational spectra. So molecules having permanent dipole moment. For example, NaCl, HCl, carbon monoxide. So these are also called as microwave active, and CCl4, H2, O2, CO2. They are called as microwave inactive. And we talk about vibrational spectra. So vibrational spectra occurs in when there is change in dipole moment during motion. So change in dipole moment during motion. Example: HCl, NaCl, carbon dioxide, sorry, carbon monoxide, CCl4, CO2. These are infrared active. However, if you talk about electronic spectra, all molecules, electronic spectra, all molecules exhibit electronic spectra because during electron transition, the change in dipole moment result in electronic spectra. So that is due to transition of electrons. Now another concept related to Frank-Condon principle is also discussed. Frank-Condon principle. So according to Frank-Condon principle, the electronic transition occurs so fast that the so quickly that the nucleus of the molecule they don't have time to move during the transition. Electronic transition occurs so quickly that the nuclei of the molecule do not have time to move during transition. So um, um, why it is so? Because electrons are much lighter than nuclei, so electron tend to move faster. So during the transition, the electron jump instantly to another energy state. So the nuclear position is generally remains fixed. So in vibrational, suppose we are drawing in spectral line. Suppose this is an electronic label, it contains a number of vibrational label, and the transition if it is occurring. So transition is given as straight vertical lines. So no change in position, no change in position. So the transitions are basically given as vertical lines. And also related to intensity, it says that the intensity of the transition depends upon the overlapping of the levels. Greater is the overlapping, greater is the intensity. So generally the transition involving bottom states or bottom levels, they tend to have greater intensity than the other transitions. So all these were a few concepts that was covered in this week's lecture. So now let's start solving a few sample problems based on the concept that we discussed. So this is question number one. Question number one says, so question number one says, for two diatomic rigid molecules, the rotational constants are same if R1 and R2 are the interatomic distances of the molecules and mu1 and mu2 are the reduced masses respectively. Then options are option A. We need to find out the relation between mu1 R1 and mu2 R2. So mu1 by R1 equal to mu2 by R2, mu1 R1 square equal to mu2 R2 square, mu1 divided by R1 square equal to mu2 divided by R2 square, or mu1 mu2 equals to R1 R2. So here it is related to the concept of rotational spectra. So in the question, here it says there are two diatomic rigid molecules and the rotational constants are same. So they have same rotational constant and their interatomic distance. Suppose this is molecule 1, this is molecule 2. R1 is the interatomic distance of molecule 1, R2 is the interatomic distance of molecule 2, and the reduced masses are mu1 and mu2. So what will be the relationship between mu1 and mu1 R1 and mu2 R2 when they have same rotational constant, that is B. So B is same. So B1 equals to B2, and we need to find out which will be the correct option. So I'll give you a few minutes and then we will discuss what will be the correct answer. So if we solve it, in the question it is mentioned B is same for both the molecules. So we know the rotational constant B, it is equals to H divided by 8 pi square IC, and we know I is mu r square. So that implies B is H divided by 8 pi square mu r square c. So when b1 equals to b2, then we have I1 equals to I2, that implies mu1 R1 square equals to mu2 R2 square. So the correct answer will be option B, mu1 R1 square equals to mu2 R2 square. Now I move to question number 2. I hope this was clear to everyone. Now question number 2 says, for a non-rigid diatomic molecule, the rotational energy difference between two consecutive labels J and J plus 1 in terms of wave number is, where D is the centrifugal distortion constant. So here we need to consider the concept of rigid, non-rigid diatomic molecule, and here it is said the rotational energy difference between the two consecutive labels J and J plus 1. So what will be the energy difference between the two consecutive labels J and J plus 1 in terms of the um, in terms of wave number. So all these are in wave number units, and B is called as rotational constant, we all know, and D is centrifugal distortion constant. Centrifugal distortion constant. And there are two consecutive labels J and J plus 1, and we need to find out the rotational energy difference between these two consecutive labels. So the options are option A J plus 1 into B minus 2D J plus 1 square, option B 2J plus 1 B minus 2D J plus 1, option C 2J plus 1 B minus 2D J plus 1 square, or option D 2 into J plus 1 B plus D into J plus 1 square. So these are the four options, and we need to find out the correct one. So I'll give you a few minutes and then we'll discuss what will be the correct expression for the energy difference between the two consecutive labels in wave number, in terms of wave number. So we know uh, uh, the expression for energy of a rotational label with rotational quantum number j. When we need to when we consider the non-rigid diatomic molecule, then what will be the energy? So the energy is given as Ej equals to B j into j plus 1 minus d j square into j plus 1 square. So this is the expression for energy. Rotational energy non rigid rotator. So now what will be the energy difference between the two labels with having two consecutive labels basically. So for two consecutive labels the quantum numbers are j and j plus 1. So what will be E j plus 1 minus Ej. So B j plus 1 into j plus 2 minus D, sorry, j plus 1 square into j plus 2 square minus B j into j plus 1 plus D j square into j plus 1 square. So if we take B j plus 1 common, B into j plus 1, then it will be j plus 2 minus j. Then again if we take minus D j plus 1 square common, then it will be j plus 2 square minus j square. So it will be B, so j gets cancelled out, so it will be 2b j plus 1 minus d. So it will be j plus 1 square. So we can put the formula of a square minus b square here, a plus b into a minus b. So j plus 2 minus j into j plus 2 plus j. And if we write it, it will be how much? Delta E, it will be 2b j plus 1 minus, it will be j plus 2. So it will be j plus 2 a square minus b square a plus b into a minus b. So j plus 2 minus j plus 2 plus j. So this is j plus 1 square, j plus 2 minus j, so it is 2, and again this is 2j plus 2, so it will be 2 common, taking 2 common, so here it will take 1 2, here it will take another 2, so it will be 4 into j plus 1, so it will be 4d j plus 1 square into j plus 1. So if we take 2 j plus 1 common, so it will be b minus 2 d j plus 1 square. So if you see the options, it will be 2j plus 1 common, b minus 2d into j plus 1 square. So 2j plus 1 b minus 2d into j plus 1 square. So correct option will be option C. So simply we need the formula for non-rigid rotator, because we need to consider the centrifugal diffusion constant here. So if you put the expression for rotational label of a non-rigid rotator, then we can calculate the energy difference between two consecutive labels. So in this way we can find, so the correct answer is 2 into j plus 1 b minus 2d j plus 1 square. Now we move to question number 3. Question number 3 says, which of the following molecules show electronic spectra? Options are, sorry, the molecules are carbon monoxide, carbon dioxide, sodium chloride and hydrogen. So options are option A, carbon monoxide and sodium chloride, Option B, carbon dioxide and hydrogen. Option C, carbon monoxide, hydrogen and sodium chloride, or option D, all of the given list. So, regarding this question, we have already discussed in today's interact session before solving the problem. So, we briefly discussed about the concept covered, and from that discussion, you can easily get what will be the correct answer. But so after a few minutes, we will discuss and we will find out what will be the correct option of this question number 3. So, so as we have already discussed in the beginning of the today's session. So since the molecule, in case of molecules, the electronic transitions lead to the electronic spectra because due to the electronic transition, they are always accompanied by the change in dipole moment. So all the molecules they give electronic spectra. So the correct option will be all of the given list because why? Now due to electronic transitions, so electronic transitions are always accompanied by the change in dipole moments. So all the molecules in the given list they will show electronic spectra. So all molecules show electronic spectra. Now come to question number 4. Question number 4 says when a white light is scattered from a liquid, a strong absorption line is seen at 3100 Armstrong and two emission lines are observed. One of these emission lines is of 4000 Armstrong, then the wavelength of another emission line is, so options are option A 13,777.7 Armstrong, option B 12,400 Armstrong, option C 9465.5 Armstrong, or option D 8907.7 Armstrong. So here the question says, so the when a white light is scattered from a liquid, a strong absorption line is seen at 3100 Armstrong. So the energy of the absorption photon will correspond to 3100 Armstrong, and this absorption corresponds to two emission lines. So one emission line is at 4000 Armstrong, so another emission line, the wavelength we need to find. So the absorption occurred at 3100 Armstrong. So there were two emission lines. So one is at 4000 Armstrong. So 3100 is less than 4000 Armstrong. So the energy of the absorption component is more than the energy of emission. So there will be another emission. So we need to find out what will be the wavelength of that emission line. So I'll give you a few minutes and then we will discuss what will be the correct answer and how we can find out the uh, emission line or the second emission line wavelength. So, if we solve this question, so the question says, so there was a strong absorption line corresponding to 3100 Armstrong, and after that there are two emission lines. So, the energy of the absorption line is corresponds to the total energy of the emission line. So, because the total energy that will be absorbed, it will again get emitted. So, there are single absorption and two emission. So, let's find out what is the energy corresponding to the absorption. So, absorption energy. So we know, so there is an expression to convert the wavelength which is given in Armstrong to electron volt unit of energy, which is given as E in electron volt will be 12,400 divided by wavelength in Armstrong. So here the wavelength is 3100 Armstrong, so it will be 12,400 divided by 3100, so it will be 4 EV. So this 4 EV will again get emitted. So we have one emission corresponding to 4,000 Armstrong. So first emission energy, it will be E1, we can say. In terms of EV, it is 12,400 divided by 4,000. This is 3.1 electron volt. So the remaining energies, so remaining energy is 4 minus 3.1, that is 0.9 ev. Now we need to find out what will be the wavelength corresponding to 0.9 ev. So the wavelength in Armstrong will be 12,400 divided by 0.9. So it will be how much? 13,777.7 Armstrong. So the remaining energy of 0.9 ev will be corresponding to 13,777.7 Armstrong. So the total absorption energy for EV, it is getting emitted in two components. One is 3.1 EV, another is 0.9 EV. So 3.1 EV corresponds to 4,000 Armstrong, and 0.9 EV corresponds to 13,777.7 Armstrong. So higher will be the energy, lower will be the wavelength, and higher will be the frequency, because E is direct proportional to frequency and E is inversely proportional to wavelength lambda. I hope this is clear to everyone now. So the correct option will be option A, 13,777.7 Armstrong. Now we move to question number 5. So question number 5 says, match the typical spectra of suitable molecules with the corresponding wave number range. So column 1 we have rotational spectra, vibrational spectra and molecular dissociation, and in column 2 we have 300 to 3000 centimeter inverse vibration, and 2i is 1 to 100 centimeter inverse, and column 3 10 to the power 6 and above centimeter inverse. So we need to match the two column. So options are 1i, 2, 2i, 3, 3i. So these are the four options, and we need to find out what will be the correct option. So here the column 1 shows the type of the spectra, and column 2 shows the wave number corresponding to that spectra. So I'll give you a few minutes, and then we'll discuss what will be the correct combination of the spectra and corresponding wave number. So vibrational wavelength. So we know rotational spectra has lower energy than vibrational spectra. So vibrational, the wavelength of vibrational spectra will be uh, more, and the wavelength of rotational spectra, so the wave number of rotational spectra will be less. So vibrational spectra corresponds to 300 to 3000 centimeter inverse. Rotational spectra corresponds to 1 to 10 centimeter inverse, and the molecular dissociation has maximum energy. So molecular molecular dissociation corresponds to high energy. So it will be having maximum wave number, so 10 to the power 6 centimeter and above. So this is rotation spectra is 2, 2 is 1, and 3 is 3. So 1 is 2i, 2 is I, and 3 is 3i. So 1 is 2i, 2 is I, and 3 is 3i. So the correct option is option B. Now question number 6. Question number 6 says, taking degeneration into account, the number of molecules in the jth level is given by nj equals to n0 2j plus 1 exponential minus bhc j into j plus 1 divided by kt, where n0 is the number of molecules at j equal to 0 level and other notations have their usual meaning. Find the value of the j for which the population of molecule will become maximum at a given temperature T Kelvin. So the options are option. So these are the four options given, and we need to find out the value of j for which nj will be maximum. So nj maximum means dnj by dj equals to 0, and when you equate it to 0 we can get the value of j for which the population of the molecule will become maximum at a given temperature T Kelvin. So I'll give you a few minutes and then we will solve to find out what will be the correct option. Okay, so when we solve it, so the question says by taking the degeneracy into account, we have the expression for the number of molecules in jth level, and we need to find out the value of j for which the value will be maximum at a given temperature T. So, in order to find out the value of j, we need to equate the first derivative of nj with respect to j to be 0 because it is uh, given that it should be maximum. So the dnj by dj will be 0. So now let's calculate dnj by dj. So it will be 2 exponential minus bhc. So nj, let me write. So nj is n0 2j plus 1 e to the power minus bhcj into j plus 1 divided by kt. So it will be 2 exponential bhc by kt j into j plus 1 plus 2j plus 1, then it will be minus bhc by kt j into j plus 1 into exponential minus bhc by kt j into j plus 1 is equals to 0. So we can take this exponential term as common, so we can omit this from both the terms. So it will be 2 minus j into j plus 1 bhc by kt into 2j plus 1 equals to 0. That implies 2j plus 1 square bhc divided by kt equals to 2. 2j plus 1 square equals to 2kt divided by bhc. So 2j plus 1 will be root over of 2kt divided by bhc. So j will be 2kt divided by bhc root over minus 1 divided by 2. So that is half 2kt by bhc root over minus 1. So the correct answer will be half 2kt by bhc minus 1. So half 2kt by bhc minus 1. So the correct option will be option A. Now we move to question number 7. Question number 7 says the expression for second overturn in vibrational absorption spectra in terms of wave number, that is centimeter inverse, of a diatomic molecule having anharmonicity xe is. So here we need to consider the anharmonic oscillator concept because we need to consider the anharmonicity xe of the molecule. So we need to find out the second overturn in the vibrational absorption spectra. So we know the second overturn corresponds to the transition from V equals to 0 to V equals to 3, V equal to 0 to V equal to 3, because V equal to 0 to V equal to 1 corresponds to fundamental harmonics, then fundamental frequency. So V is equal to 0 to V equal to 2 corresponds to first overturn. So V equal to 0 to V equal to 3 corresponds to second overturn. So you need to find out the wave number corresponding to the transition V equal to 0 to V equal to 3, and you need to consider the concept of anharmonic oscillator because in the options also they are given in terms of anharmonicity xe. So we need to consider the anharmonicity of the molecule. So I'll give a few minutes and then we'll find out what will be the correct answer. So the second overturn corresponds to the transition from v equal to 0 to v equal to 3. So now if we calculate, so in terms of an harmonic oscillator, an harmonic oscillator, we have the energy corresponds to the quantum number v is v plus half nu e minus v plus half square xc nu e. So when E0 to E3 transition occurs, so delta E, it will be 3 plus half nu E bar minus 3 plus half square xc nu E bar minus half nu E bar plus 1 by 4 xc nu E bar. So it will be 7 by 2 nu E minus 1 by 2 nu E plus, sorry, plus 1 by 4 xc nu E minus 49 by 4 xc nu E bar. So it will be 7 by 2 minus 1 by 2 nu E plus 1 by 4 minus 49 by 4 xc nu E. So it will be 3 nu E minus xc nu E into 12. So if we take 3 nu E bar common, it will be 1 minus 4 xc. So the correct option will be option C, 3 nu E into 1 minus 4 xc. I hope this is clear to you. Now we move to question number 8. Question number 8 says the energy difference in rotational spectra between j equal to 1 to j equal to 2 levels in terms of wave number, that is in terms of centimeter inverse, for a non-rigid diatomic molecule in terms of rotational constant B and centrifugal distortion constant D is. So options are option A 2B minus 4D, option B B minus 8D, option C 4B minus 32D, or option D 2B minus 16D. So here we need to again consider the non-rigid rotator concept. Rotation constant B and rotational and distortion constant D is given, and we need to find out the energy difference between the two labels j equal to 1 and j equal to 2. So I'll give a few minutes and then we will discuss what will be the correct answer. So again, uh, we know the expression for energy is B J into J plus 1 minus D J square J plus 1 square. So this is the formula for energy. Now when the transition occurs from E J plus 1 to E J, then it will be, we have already discussed, it will be 2B J plus 1 minus 4D J plus 1 square. So when J is 0, J plus 1 is 1, then what will be? So it will be 2B 0 plus 1 minus 4D 0 plus 1 square. So it will be 2B minus 4D. So the correct option is option A. Sorry. So this was 0 to 1. So 2B minus 4D. But in the question it is given 1 to 2. So J equals to 1 to J equals to 2. So new J bar will be 2B 1 plus 1 minus 4D 1 plus 1 square. So 4B minus, this is J plus 1 cube, not J plus 1 square. So it will be cube. So it will be 4D into 8. It will be 4B minus 32D. So correct option is option C, 4B minus 32D. Now I move to question number 9. Question number 9 says, when 310 Armstrong radiation is used to produce photoelectron spectra of neon, photoelectrons of kinetic energy 18 electron volt have been emitted. Find the ionization energy of these electrons. Option A 40 electron volt, option B 18 electron volt, option C 22 electron volt, or option D 58 electron volt. So now again this type of question we have already solved. So now we need to find out what is the electron volt energy, what is the energy in terms of electron volt corresponding to 310 Armstrong. Then we have electron energy 18 electron volt. So the remaining energy will be the ionization energy of these electrons. So how we will find? So we know the radiation energy will be, the radiation energy, it will be 12,400 divided by 310. So which is coming out to be 40 electron volt. So 40 electron volt is the total energy. So this 40 electron volt, it will be equal to electron kinetic energy plus ionization energy. So 40 electron volt is 18 electron volt plus ionization energy. So that implies the ionization energy will be 40 minus 18 equals to 22 electron volt. So the correct option is option C, 22 electron volt. Now we move to the last question of today's interaction session, question number 10. Question number 10 says, which of the following spectra ranges fall in ultraviolet region? Options are option A, 4000 Armstrong to 7500 Armstrong, option B, 200 Armstrong to 2000 Armstrong to 4000 Armstrong, option C, 10 meter to 100 meter, option D, 0.1 Armstrong to 100 Armstrong. So we need to find out which of these range fall in ultraviolet region. So I'll give you a few minutes and then we will discuss what will be the correct answer. So we know in electromagnetic spectrum different regions are arranged in terms of their wavelength and frequency, and we know for visible region the wavelength will be more, for ultraviolet region the wavelength will be less. Then for radio waves the wavelength will be again higher, and the least wavelength will be of X-rays. So for X-ray the wavelength range corresponds to 0.1 Armstrong to 100 Armstrong. For UV, it is 2000 to 4000 Armstrong. For visible, it is 4000 to 7500 Armstrong, that is 400 nanometer to 750 nanometer. And then for radio waves, the wavelength is more, 10 meter to 100 meters. So the ultraviolet region corresponds to the wavelength 2000 to 4000 angstrom. So the correct answer is option B. So with this we come to the end of today's interaction session. So in this interaction session we solved a few problems related to the week 11 course content, and the next interaction session we will be solving a few problems related to the week 12 of the course, which will be our last regular interaction session. However, the last interaction session is on next Monday. However, an extra session I will take on Tuesday, the next day itself, where I will cover, basically I will revise all the concepts taught in this course, like both atomic spectra and molecular spectra. That will give an overview of the course, as well as it will be helpful for revision if you are appearing for the exam. With this I come to the end of today's interaction session. Thank you all.